the amount of incoming data that we expect is coming in loads and loads of, the velocities is huge. So it needs to be fast. So we took images of size 256 times 256 pixels, and we used both PyBDSF, which is the ground truth, as well as UNet to create masks. In creating the masks, we were recording the time it takes to create the mask. So for UNet, it takes 16 seconds to produce masks for 100 images. And for PyBDSF, it takes approximately 200 seconds to produce masks for 100 images. And as we can see from the two graphs, UNet is gradually increasing, but not steeply. But with PyBDSF, the amount of time that it takes to produce a mask images of 500 images is approximately like 900 seconds, which is, I'm not quite sure of the number of minutes. But this is a selling point for this work because of the amount of time it takes to produce mask image using UNet. So we used OpenCV detection model to go into the image. Once the image is segmented, we draw a border around it, making it easier for astronomers to see where exactly the radio sources are. So we took an image of size 9,000 times 9,000 pixel. We threw it into the model, and it created borders around each and every radio source. Not quite sure if it's visible, but I just made a highlight of what is happening in that clustered middle area. UNet performs quite well, but there are improvements that could be made to the model. For instance, the fact that we use PyBDSF as a ground truth is a limitation. So labeling Meerkat data by hand, which would be quite tedious, would do us good as our accuracy will not lean more towards PyBDSF as we use it as the ground truth. And the future plans is to classify all the radio sources in the image. As you have seen in the previous image, a border is drawn around each and every radio source. So classifying which class each source belongs to would be a great idea. And creating a catalog that will contain of an individual source, the name of the source, the class it belongs to, as well as the location. The impact of this work would be a potential pre-processing automation step for astronomers. So it would alleviate the amount of time that they need to go into an image and identify each source. And it is faster than the current models that are, well, PyBDSF. That is a popular method that they're using to segment radio sources or find radio sources. And converting an image with millions of radio sources into potentially a catalog with individual sources will make it easier, and classed data that will be ready for scientific investigation. This is the team that I was part of in my master's, the radio astronomy tools and techniques. And this is one of the busy weeks that we had at Rhodes University. As you can see, we are really busy doing our masters. And I got the privilege to be funded by Sarao, and the university that I was affiliated with is Rhodes University. Thank you. Here is a list of all the references that I have used for the presentation. Thank you. Any questions? Yes. I think there's no. Yes, it was based on CPU. We had like 500 images. So we're gradually increasing the images while checking the performance. Where do I see the questions?
I'm taking over Jason's work.
Did you schedule time on the Meerkat using the OPT? No, I got readily made images, so the images were already available for me to use. Yes.
Thank you for this. On the slide that precedes the experiment results with the graph.
This one? This one?
Okay, it's not there yet. It has the graph.
Oh, I'm not sharing my screen.
Yes, that one.
This one,
No.
yes.
Yes, that one. Yeah, that one. Time to run. Okay, that's in seconds. Okay. Okay, then.
Okay.
Despair, where was that? Where did you guys do that? Was it provided by the university? The hardware you used for the test?
No, we're using it. Actually, yes, because we're using the road servers.
Oh, okay.
Yes, Nadim?
Thanks. Regarding your future work, you mentioned about putting human in the loop, okay, to label the data. And we human, we always make mistake. Can you find another way of doing that to remove the human subjectivity?
I am not quite sure if we could, because currently it's astronomers that know the morphology of radio sources. So it would be easier if they are the ones that label what is a radio source and what is not within an image. So I'm not quite sure if there's another method that we can use to eliminate the human interaction. Are you suggesting something?
Yeah, there are lots of other models that have come, like especially when you're talking about your pi BDSF for your ground truth.
Yes.
I mean, this itself is an algorithm that has many knobs to tweak and different ground truth version you can get.
Okay.
So yeah, maybe trying to look at new methods that people have used and then cross compare from simulation.
Okay.
Where you know where you have put your source yourself, rather than taking the images and then, tune your model accordingly. Yeah.
Okay, thank you for that input. We'll take that into consideration when writing a paper.
So to ask, your test and your training data, there was a split, a 70-30 split.
Yes.
Is there significance related to that split? Could it be 60-40? I'm not too sure if something maybe, yeah, I just want to know why you actually chose that split.
It could be 60-40 or 60-30-10, but I just use 70-30 is another popular split where you use most of your data to train and then less of it to test. Yeah. Yes, Nadim? Yes.
So you train and test your algorithm.
Yes.
So you did not validate your algorithm, your model.
No.
I think it'd be good to have a training, then you validate, you take a subset of your data to validate your model, so that you can tune, their parameters with a validation data set. And then afterwards, you throw in your test data, the unseen data, and see how it works. So doing a train, validate, tests, like 70, 15, 15, or 60, 40, 20, 20.
Okay.
Yeah.
Because the method that we used was we used epochs. So in training the model, we didn't take all the data and put it into a model. We used different sets of epochs. So an epoch is the time it takes to run through the whole training set. So we take subsets of that, or yeah. Yeah. Any more questions? Yeah. Oh yes, Oleg.
Did you try visualizing what's going on in the intermediate layers there?
No.
It would be fun, I think, and because at the moment this whole thing is like a black box, right?
Yes.
It would be really interesting to kind of understand what it's actually doing there.
The weights. Okay. I can visualize what was happening using the weights that I have collected. I'll take one more question.
Oh, okay. Just to get something. So your model tries to find the locations and identify exactly what kind of source is that. Right?
It's classifying pixel by pixel.
Yeah.
If a pixel belongs to a certain class, that there are two classes, it's a binary classification. So for each and every pixel within the 256 times 256 pixel, it will say that this pixel belongs to the background or it belongs to a source.
Oh, so your output layer of the CNN is a binary class, right?
Yes.
So why softmax not sigmod? So why did you choose to use the softmax or different function?
Softmax is usually used for binary classification. Sigmoid would be used when you have multi-classes. So the model that converts pixels into probabilities and is good for binary classification is softmax. We use it because a softmax is outputs a value between 0 and 1, and 0 and 1 can be used as probabilities. So we cannot use a sigmoid because a sigmoid also has negative values, and it it doesn't have negative values, but with the bounding between 0 and 1, then we can get probabilities that will be used for the different classes. Thank you so much.
Yeah. Fellow colleagues, yeah, thank very much, Ms. Chava. I think that was very informative and amazing and well presented. Fellow colleagues, as software team, no, as software team, we appreciate constructive feedback. So if you having constructive feedback, please give to Ms. Chava. I'm pretty sure she's definitely going to appreciate that, as this is another way for us to really get to the next level. Thank you very much for making time to attend Ms. Chava's talk. It was amazing.